Imagine a massive big box retailer
Right.
somewhere in the Midwest. It's just a random Tuesday. And a customer walks in and buys 2 extra units of a standard product.
Like a blender or something.
Yeah, exactly. It's a specific brand of blender. That is it. Just 2 extra blenders. But by Friday, because of those 2 blenders, a manufacturer like 1,000 miles away is panic ordering an entire warehouse full of raw steel and microchips.
Which they are never, ever going to use.
Right.
It sounds totally absurd when you put it like that, but I mean, that scenario plays out every single day in the real world.
It's wild.
It's the invisible force that bankrupts companies. It causes massive global shortages.
So today, we are diving into exactly how that happens, and more importantly, how businesses actually stop it from happening.
Yeah.
Welcome to the deep dive. Whether you are studying for your CPIM, so that's the Certified in Planning and Inventory Management exam, basically the gold standard for supply chain folks, or, you're just an insanely curious mind who wants to fundamentally understand how the world makes things, this session is custom tailored for you.
Absolutely. Because we are looking at the foundational blueprints of modern supply chains.
Right.
We're going to explore how a business decides to build a product, how they physically organize their factory floors to survive, and even how these exact same principles apply to designing services, like software or consulting.
Okay, let's unpack this, because if I'm starting a business, my first thought is usually just, hey, I have a great product, let's build a factory.
Oh, yeah.
I mean, we can't just walk onto a dirt lot and say, cool, let's put a conveyor belt right here. There has to be a broader operational strategy first, right?
That is the most common and honestly often the most fatal mistake a new manufacturer makes.
Really? Just building it?
Yeah, because you cannot design a physical space until you understand your relationship with customer demand. Every single operational decision, from where you bolt a machine to the floor to the exact hour you order your raw materials, it's all a physical manifestation of a high-level corporate strategy.
Ah, okay.
And before you decide how you are going to physically build something, you first have to decide when you're going to build it.
Okay, which brings us to, I guess, the ultimate supply chain philosophical debate.
Push versus pull.
Yes, push versus pull. Let's ground this a bit. Let's say I've invented this revolutionary new product, a temperature-controlled, Bluetooth-enabled travel mug.
Nice.
Yeah, let's call it the Magenius. So if I adopt a push operational strategy from Magenius, what exactly am I doing?
Well, if you run Magenius as a pure push environment, which is also known as a forecast-driven enterprise, you are essentially operating on educated guesses. You look at historical data, market trends, maybe, some seasonal weather patterns, and you build a forecast. You say to yourself, we believe we will sell 100,000 Magenius units this coming winter.
So then I just tell my factory to start making 100,000 mugs right now?
Yes. You push those raw materials into production, then you push the finished mugs into inventory, and then you push them out to regional distribution centers.
Wow, good.
And all of this happens before a single actual customer has swiped their credit card.
That feels incredibly risky.
It is. You are building to a prediction, not to reality.
Right, because the danger there is just so obvious. What if my forecast is completely wrong? What if, I don't know, a competitor releases a cheaper mug, or the winter is unusually warm and nobody wants hot coffee? I'm sitting on a mountain of mugs.
That is the capital risk.
Yeah.
I mean, a push strategy is essentially a company placing a massive multi-million-dollar bet against the future.
And if I lose the bet?
If you're wrong, your cash is trapped. It's trapped in plastic and heating coils sitting in some warehouse in Ohio.
Right.
But it actually gets much worse than just excess inventory.
Wait, worse than losing millions of dollars in trapped inventory?
Oh, yeah. A flawed forecast in a push system creates this cascading operational nightmare. It's known as the bullwhip effect.
The bullwhip effect. Yes, it's such a visceral name. So going back to my intro with the 2 extra blenders on a random Tuesday, let's break down the mechanics of this. How does a tiny fluctuation at a retail store turn into a massive swing for my Magenius factory?
So let's visualize an actual bullwhip.
Okay.
A tiny flick of your wrist at the handle creates a massive violent crack right at the tip.
Yeah.
In our scenario, the handle is the retail customer, and the tip of the whip is your raw material supplier.
Try and let you.
So let's say a big electronics retailer typically sells 10 Magenius units a week. But suddenly there's a slight uptick. They sell 12 units.
Just a 20% increase? That's nothing crazy.
Right, it's tiny. But the buyer at that retailer who is operating in a push model, they get nervous.
Because they don't want to run out.
Exactly. Their internal metric is never stock out. So to buffer their own inventory, just in case this trend continues, they don't just order 12 from their distributor. They order 15.
Ah, so they are padding the order out of fear.
Exactly. Now, the regional distributor sees an order for 15. They think, wow, Genius demand is surging in the Midwest.
Oh, no.
Yeah. And to protect their own service levels and maybe to hit a threshold for some bulk freight shipping discount.
They pad their order, too.
Yes. They order 20 units from you, the manufacturer.
And I'm sitting there looking at my dashboard, and I see an order for 20, which is double the historical norm.
Okay.
So I panic, I adjust my master production schedule, and I order enough microchips and raw steel to make 30 units.
And there's your bullwhip crack.
Wow.
A tiny 2-unit increase in actual consumer demand just rippled backward. And it was amplified by fear in batch ordering at every single node.
Resulting in me drastically overproducing.
Exactly. And what happens when the retailer's demand drops back down to 10 the very next week?
I am completely stuck. I've bought 30 units worth of parts, my warehouse is overflowing, my inventory holding costs are just bleeding me dry, and the whole system chokes.
It's a disaster.
So how do we stop the bullwhip effect? Because obviously companies still use forecasts today. They haven't all gone bankrupt.
Right. The antidote within a push system is radical visibility.
Meaning what?
The manufacturer needs to see the actual point-of-sale data from the retailer's cash registers, not just the distorted, padded orders coming from the distributor.
Oh, so if I had seen that the retailer only actually sold 12 mugs,
Yes.
and maybe I knew that they ran a little weekend coupon promotion, I wouldn't have panicked and ordered materials for 30.
Exactly. It's about relying less on siloed forecasting and more on shared real-time data across the entire supply chain.
Makes sense.
Yeah.
But even with great data, forecasting is inherently flawed. Nobody has a crystal ball, which perfectly sets up the alternative.
Right.
If guessing the future is a recipe for the bullwhip effect, we shift to the pull system.
Yes, the demand-driven enterprise. This was famously pioneered by Toyota.
Right.
In a pull system, the supply network is reacting to actual demand.
Okay.
You do not produce a product until a downstream customer actually signals that they need it. The customer pulls the product through the system.
Okay, I love the idea of this. The core goal here is that I don't have millions of dollars sitting in a warehouse hoping someone buys my mugs. I am lean. I only build what is literally already sold.
That's the dream.
But I have a huge problem with this in practice.
Which is?
It sounds like trying to cook a massive Thanksgiving dinner, but refusing to buy the turkey until your guests are actually sitting at the dining room table. I mean, if I wait for a customer to order a Mud Genius before I do anything, my lead time, the time the customer has to wait, is going to be like 6 months while I mine the raw materials in Asia and ship them over. Nobody is waiting 6 months for a coffee mug.
That is a phenomenal analogy.
Yeah.
And it highlights exactly why a pure pull system is functionally impossible for most consumer goods.
Right.
You cannot go to the turkey farm when your guests are already holding their forks.
Exactly.
This is why modern operations rely on a hybrid mechanism. It's called Demand-Driven Materials Requirements Planning, or DDMRP.
DDMRP. Okay, demystify that acronym for me. Because supply chain professionals throw that around a lot. What is it actually doing?
Think of DDMRP as setting up fire breaks in a forest.
Okay.
If a massive spike in demand catches fire, a pure pull system would let that fire burn all the way back to the raw material supplier, causing total chaos.
Right.
DDMRP stops the fire by placing dynamic strategic inventory buffers at very specific points in your supply chain.
Dynamic strategic inventory buffers. So just piles of strategic stuff.
Exactly. Piles of stuff, but they are shock absorbers. Let's look at your Mud Genius. You don't build the final mug until the customer orders it, but you do maintain a strategic buffer of pre-assembled heating coils and Bluetooth chips.
Ah, I see.
And these buffers are dynamic, meaning their size grows and shrinks based on real-time daily demand signals, not some static annual forecast.
Yeah. So when the customer pulls the trigger and orders a mug, the demand signal only has to travel back to the nearest buffer my pile of pre-assembled parts.
Yes.
It doesn't have to travel all the way to the microchip fabricator in Taiwan.
Precisely. It kills the bullwhip effect dead in its tracks.
Yeah.
And the point where you place that buffer is called the push-pull decoupling location.
The decoupling location, meaning the exact geographic or operational point where my strategy switches from guessing to reacting, from push to pull.
Exactly. Everything upstream of that decoupling point is pushed. You are forecasting and building inventory of components.
Got it.
But everything downstream of that point is pulled. You are reacting to specific customer orders. And where a business places that decoupling point, well, that dictates their entire manufacturing environment.
Which brings us to the TO spectrum.
Yes.
Depending on where I plant that decoupling flag, my business falls into one of 4 primary environments. This is the product process matrix.
This is where the abstract strategy hits the physical reality. These environments are defined by a severe trade-off between volume and variety.
And how that impacts the customer's lead time, right?
Exactly.
Let's walk through these 4 environments. Let's start with the one that leans the most toward a push strategy. Make to stock, or MTS.
Make to stock is basically the grocery store aisle. You are making products to put them into stock on a shelf. High volume, very low variety.
Okay.
The product design is fixed. You might have several different stock keeping units or SKUs, so maybe your Magenius comes in black, white, and silver, but the customer cannot change the core design.
The capital risk here is astronomical, like we discussed.
Okay.
But the customer lead time is the best in the world.
Right, it's instant.
You just walk into the store, grab the black mug off the shelf, and you're done. The wait time is 0.
Because the decoupling point where push meets pull is right there at finished goods inventory.
Wow.
You push the production, the assembly, the shipping, all based on a forecast. The customer only pulls it when they physically pick it up. Your expert planning here relies purely on forecast reliability, and your control metric is your customer service level. Did we stock out?
Okay, now let's say I want to offer my Magenius customers more variety, but I still want to be fast. I move one step along the spectrum to assemble to order, ATO.
Here we see a massive shift. Volume is still medium-high, but variety increases to medium-low. We are dealing with customized configurations of standard components.
Like what?
Think of buying a laptop online. You pick the processor, the memory, the screen size,
Yeah.
but you are picking from a predetermined menu.
Oh, I see. So for my mugs, maybe you choose the body color, the lid style, and the battery size.
Exactly. And look at how the physical flow changes here. You are no longer pushing finished mugs into a warehouse. The decoupling point has moved backward.
Okay, where to?
Your push stops at work in process, or WIP, inventory. You forecast and build a massive pile of standard bodies, lids, and batteries, but you do not snap them together until the customer clicks buy.
So the lead time is slightly longer than make to stock because I do have to physically assemble and ship it.
Right.
But the trade-off is I offer a custom product without the insane inventory risk of trying to guess exactly how many red mugs with large batteries people are going to want this season.
What's fascinating here is how the location of the inventory shifts entirely across these models.
Yeah.
From an information standpoint, ATO planning is all about configuration management, making sure you have the exact right mix of components in WIP so you can quote an accurate lead time to the buyer.
Okay, so moving further down the variety spectrum, what if my customers want something I haven't pre-designed at all? We hit make to order MTO.
MTO represents medium-low volume and medium-high variety. You are creating truly unique configurations. This isn't picking from a menu. This is a customer providing specific requirements.
So maybe a corporate client wants like 500 Magenius units with their custom logo embossed right into the steel, painted in their exact corporate Pantone color.
Yes, and the decoupling point moves all the way back to the raw materials.
Oh, wow.
You push raw steel and blank microchips into inventory based on a general forecast, sure, but you don't produce or assemble anything until that specific corporate contract is signed.
And because of that, the customer cycle length is long. They have to wait for actual production to occur.
Exactly. For an MTO company, planning relies heavily on engineering specifications and costing. You need to know if you actually have the machine capacity to stamp that custom logo without completely disrupting your other orders.
Okay, finally, we reach the extreme end of the spectrum, which is engineer to order, ETO. This is low volume, incredibly high variety.
ETO is building a specialized suspension bridge, or a custom cruise ship. Or in your case, maybe NASA hires you to build a single zero-gravity coffee containment system for the space station.
I am definitely not keeping zero-gravity parts in my warehouse.
Obviously not. In ETO, the decoupling point is basically at the conceptual design phase. You aren't pushing anything based on forecasts, except maybe keeping highly skilled engineers on your payroll. Every single physical step designing, purchasing the exotic materials, production, assembly is pulled by that one unique contract.
That makes total sense. The planning focus there is just pure project management.
Exactly.
But, here's where it gets really interesting for me. Because the modern business landscape doesn't always play by these rigid textbook rules.
Very true.
You look at companies today offering insane bespoke customization, but they are delivering it at mass market speeds and prices. How are they breaking the matrix?
Well, they aren't breaking it. They're hacking it through hybrid models.
Right.
One of the most important concepts for a modern supply chain is mass customization.
Mass customization.
It is the holy grail, offering the bespoke variety of a make-to-order product, but at the near-zero lead time and low cost of a make-to-stock product.
But how is that physically possible? I mean, if I'm engraving custom names on every single mug, I lose my efficiency.
You achieve it through another critical concept, modular design. You standardize the core architecture into discrete modules that snap together universally. You spend massive amounts of engineering capital up front to ensure that, say, every battery fits into every mug body perfectly.
So I'm not redesigning it every time.
Right. Modular design is the engine that allows assemble to order to actually mimic mass customization.
There was another hybrid strategy from the sources that really stood out to me: postponement.
Oh, yeah. That's a big one.
Delaying the final differentiation of a product for as long as theoretically possible.
Postponement is a brilliant strategy for managing global inventory risk. Let's say Magenius goes global, right?
Okay.
You sell in the US, the UK, and Europe.
Right.
Each region requires a totally different power cord for the charging coaster.
Right, the plugs are all different.
In a rigid make-to-stock model, you would build US boxes, UK boxes, and EU boxes at your factory in Asia, and then ship them out.
And if UK demand spikes while US demand drops, I have the wrong inventory in the wrong country, and I can't easily swap them because the boxes are already shrink-wrapped with the wrong plugs inside.
Exactly. So you use postponement. You manufacture the base Magenius unit as a standard universal item. You ship them in bulk to regional distribution centers, and you don't differentiate them until the last possible second.
So the final step, like just dropping the UK power cord into the box, is postponed until it's at the distribution center in London right before it goes on the delivery truck to the customer.
Exactly. It drastically reduces the amount of inventory tied up in specific localized SKUs. It allows you to respond to regional demand shifts instantly.
That's incredibly smart.
And the same logic applies to packaged order, like where you keep a product, maybe bulk cereal, in giant vats and only package it into specific branded boxes when an actual order requires it.
Okay, so we've figured out our strategy. I know whether I am making to stock, assembling to order, making to order, or engineering to order. I've established my TO.
You have your strategy.
But if I just drop 50 identical machines into an empty warehouse, I still just have chaos. We have to select the specific manufacturing process to execute this strategy.
Exactly. This is where we look at manufacturing process types. And just like the environments, these process types exist on a continuum dictated by that severe trade-off between volume and variety.
Let's start with the process type meant for that NASA zero-gravity mug, the project process type.
A project process is specifically designed for the ETO environment, unique, massive deliverables. The workflow is completely intermittent.
Right.
In a project process, the product is usually stationary, and you bring the resources, so the welders, the engineers, the specialized tools, to the site.
So the management focus isn't on a steady flow of identical units at all. It's entirely about controlling three specific variables: time, cost, and scope. Scope meaning the exact boundaries of what we agreed to build for the client.
It is project management in its absolute purest form. But let's say you move down the spectrum. You are doing make-to-order. You are doing custom batches of engraved mugs for corporate clients. You would use a work center process type, also known as a job shop.
A job shop. Okay, picture my Magenius factory floor. How is a work center organized physically?
A work center is characterized by grouping equipment by common function. You have dedicated areas operated by highly skilled workers. So all of your metal cutting lathes are in the north corner. All of your painting booths are in the east corner. All of your laser engravers are in the south corner.
And the product just travels between these functional centers based on its unique recipe.
Right.
So if client A wants an unpainted engraved mug, it goes from cutting straight to engraving. But if client B wants a painted non-engraved mug, it goes from cutting to painting.
And that perfectly highlights the massive downside of a work center. Because every single order has a custom routing, the workflow is inherently unbalanced. You have parts constantly crisscrossing the factory floor.
Which means queue times.
Huge queue times.
A cart of 50 mugs gets to the painting booth, but the booth is busy painting a different order, so my mugs just sit there.
That is the physics of a work center. High work in process inventory. long lead times. Managing a job shop is incredibly complex because your bottlenecks are constantly shifting depending on the exact mix of orders you get that week.
You trade efficiency for ultimate flexibility.
Exactly.
Okay, but a work center sounds exhausting to manage. If I'm scaling up my genius, how do I find a middle ground where I'm not making one-offs, but I'm also not committed to a massive, inflexible assembly line?
You transition to a batch process type?
Batch process.
Yeah. It's still intermittent,
Yeah.
but you are moving toward higher volume and lower variety.
Yeah.
Instead of making one totally unique order, you are making a batch of identical items. You run 5,000 black lids, then you stop, you change the machine tooling, and you run 5,000 silver lids.
So I have longer runs and fewer setups compared to a job shop. And I guess the worker doesn't need to be quite as highly skilled as the master craftsman in the work center, but they still need moderate skills to handle those machine changeovers.
You still have queues, and you still group machines by function, but the flow is slightly more predictable. But once your volume hits a critical mass, say, you are producing millions of make-to-stock mugs, you cross a major threshold.
What happens?
You leave intermittent processes entirely behind and enter flow processes, starting with the line process.
Ah, the classic assembly line. Henry Ford's dream.
Yes. High volume, controlled rate, discrete units. The process is completely standardized. The equipment is devoted to a specific sequence. You don't have all the lathes in one corner anymore.
Right.
We have a lathe, followed immediately by a painter, followed immediately by an assembler.
Because the rate is nearly constant, my work-in-process inventory drops to almost zero. Parts aren't waiting in bins, they are constantly moving.
Exactly.
My lead times are incredibly short, and the worker skill level drops significantly because their tasks are highly divided and repeated all day.
But the trade-off is brutal inflexibility. A line process produces one thing. If you want to introduce a totally new, square-shaped Mogenius, you can't just adjust the routing. Like in a work center, you often have to build a completely new multi-million-dollar line.
Wow, and the final process takes that rigidity to the absolute extreme, right? The continuous process type.
Think of water flowing through a pipe. Continuous processes are for liquids, gases, or bulk solids.
Like an oil refinery.
Or a paper mill, or a chemical plant. The product flows end-to-end without ever stopping. It is highly inflexible, requires extreme precision, and demands astronomical capital investment.
But the per unit cost has to be fractions of a penny because the volume is limitless.
Exactly.
So what does this all mean when we put it together? If I plot these environments and processes on a graph, what the sources call the product process matrix, what happens if I get it wrong? Let's say I have a massive hit on my hands. I am selling millions of identical standard Mogenius units. It's high volume, low variety. But for some reason, I try to produce them in a work center job shop environment. What happens to my business?
You go bankrupt. Almost immediately.
Really? That fast?
And the matrix illustrates exactly why.
Yeah.
If you plot volume on the horizontal axis and variety on the vertical axis, the ideal pairings, so ETO with project, MTO with work center, MTS with line, they form a perfect diagonal line right down the middle of the graph.
You want to live on that diagonal line.
You must live on that diagonal line. If you take a high volume, standardized product and run it through a work center, you are operating way off the diagonal.
Right.
A work center uses highly skilled, expensive labor. It has massive queue times. Your standard mug will cost $50 to produce and take 3 weeks to deliver. Meanwhile, your competitor, who is safely on the diagonal using a line process, is producing an identical mug for $5 in 3 minutes.
You will be absolutely decimated on speed and cost.
And the inverse is true, too. If you try to run highly customized, one-off engraved mugs through a high-speed line process, the constant stopping and starting to retool the line for every single custom order will destroy your efficiency.
The matrix essentially proves that your operational trade-offs, your speed, flexibility, cost, they must align perfectly with the physical physics of your chosen process.
Couldn't have said it better.
Which brings us to the actual geography of the factory. I know my process type. Now I have to actually arrange the physical machines. I have to design the process layout.
Right, because you can have the right strategy and the right process, but a terrible floor plan will still ruin you.
Really?
Oh, yeah. The physical layout dictates how material, information, and people flow through the building. The operational principles evaluate 4 primary layout choices.
The first one is pretty straightforward, the fixed position layout.
This is the physical home for the project process type. The product is simply too massive or fragile to move.
Like shipbuilding.
Or commercial aircraft assembly, or building a skyscraper.
Mm-hmm.
The ship stays in one dry dock, And all the materials, cranes, and specialized labor are brought to it.
The benefits are obvious, I guess. High adaptability, and you don't have to figure out how to put a 50,000-ton ship on a conveyor belt.
Exactly.
But the limitations are severe. Storage space around the site has to be a nightmare, and moving heavy machinery to the product is wildly inefficient.
It is necessary for ETO, but you would never use it for consumer goods. The next layout is the functional layout. And if we visualize the diagrams mapping this out, this is where a factory floor gets visually chaotic.
The functional layout is the physical manifestation of the work center job shop.
Griff.
We group machines by what they do, all the welding machines in one room, all the testing stations in another. If you were to trace the path of a product moving through this layout, it doesn't look like a straight line. It looks like a chaotic bowl of spaghetti.
Let's actually visualize that spaghetti web. Imagine your factory has 10 different functional rooms. You're producing 3 different types of custom mugs, product A, B, and C.
Okay.
Product A's recipe dictates it goes from room 1 to 2 to 3 to 4. Smooth enough. But product B has to go from room 5 to 6, back to 2, then to 7, 3, and 10.
And product C is jumping wildly from 8 to 1 to 9 to 2 to 6.
Right. They are crisscrossing, backtracking, and fighting for aisle space. Workers are constantly pushing carts of half-finished mugs hundreds of feet across the warehouse just to get to the next room.
And that physics of movement explains the massive limitations of a functional layout. Because product flows are constantly crossing, and because every room operates at a different speed, you generate massive queue times.
Exactly.
A cart of mugs arrives at room 2, but room 2 is backed up, so the mugs just sit in a bin. This leads to a huge potential for bottlenecks. Your total production time skyrockets, and your material handling costs are astronomical because you are paying workers just to walk things across the building.
So, given all that, why would anyone ever use this? Equipment flexibility. If one drilling machine in room 2 breaks down, you just route the part to the drilling machine right next to it.
Oh.
The factory doesn't stop. You also need fewer total machines because they are shared across all product lines, and you could put one highly specialized master driller in charge of supervising the entire room. It survives on flexibility.
Still, that spaghetti web of carts and queues sounds painful. If I want to optimize, but I still have distinct product families, like I make 5 types of travel mugs and 5 types of coffee thermoses. Is there an antidote to that chaos?
Yes. It is one of those powerful concepts in lean manufacturing. The cellular layout.
Cellular layout.
The transformation is incredibly satisfying. You take that chaotic spaghetti web of functional rooms and you reorganize the machines into clean, sequence-specific U-shaped cells.
Okay, explain the U-shape. Why not just a straight line?
A U-shape allows a single worker, standing right in the middle, to operate multiple machines without walking long distances.
Oh, that's smart.
It also means the entry point for raw materials and the exit point for finished goods are right next to each other, which makes loading and unloading much easier for the material handlers.
So instead of grouping all the drills together in one room, I build a dedicated cell for my travel mug family. I pull one drill, one painter, and one tester, and I arrange them in a tight U-shape.
Exactly. And you build a separate duplicate cell for your thermos family.
But wait, that means I have to buy more drills and more painters? My capital investment goes up? What justifies that cost?
The physics of time and space.
Okay.
By locating the workstations mere inches from each other in the exact sequence needed, you virtually eliminate material handling distances. The part goes from the drill directly into the hands of the painter.
There's no cart.
There's no queue time waiting in a bin. Work in process inventory vanishes. Processing time plummets.
It shrinks lead times so drastically that it essentially turns an intermittent, chaotic batch process into a smooth, miniature flow line.
Right. But the limitation is strict. It only works if your products can be grouped into distinct logical families that share a similar routing. If every order is 100% unique, you cannot design a cell for it.
Makes sense. And finally, we have the ultimate high-volume layout, the product-based layout.
This is the physical arrangement for a line or continuous process. It is a straight, linear, dedicated flow. Input, workstation 1, workstation 2, workstation 3, output.
The benefits are pure, ruthless efficiency, lowest total material handling costs, very little work in process. Because things move so fast, it actually takes up less floor space than a job shop because you aren't storing giant bins of half-finished materials.
And equipment utilization approaches 100%.
But you surrender all flexibility. If customer demand shifts to a new product, you are left holding a very expensive, very useless factory.
And the critical risk here, if workstation 2 breaks down, Workstations 3 and 4 instantly starve for parts.
And Workstation 1 gets backed up.
The entire multi-million-dollar line dies because of one broken gear.
Okay, so we've traveled from the macro strategy of guessing versus reacting, down through the environments and process types, all the way to arranging the machines on the floor. It is a perfectly interlocked cascade of decisions.
It really is.
But here is the curveball. Not every business makes a physical widget. What if my product is a service? Do these rules just disappear?
Absolutely not. Supply chain professionals deal with services constantly, whether it's managing third-party logistics providers, software vendors, or even internal continuous improvement projects.
Right.
And the exact same trade-offs apply. This brings us to service design and project management.
The operational tool for this is the service design matrix. Just like the product process matrix looked at volume versus variety for physical goods, the service matrix evaluates trade-offs in a service environment.
Specifically, it looks at the degree of contact between the customer and the service provider on the vertical axis against a severe trade-off between sales opportunity and production efficiency on the horizontal axis.
Let's ground this. Let's look at the tax accounting industry. If I look at the high contact end of the matrix, what does that look like?
High contact is an in-person, fully customizable service. You walk into a high-end, boutique accounting firm, you sit across a mahogany desk from a CPA, you explain your complex multinational corporate structure, your trusts, your investments, and they build a completely bespoke tax strategy for you.
The customer interaction is maximum, and the service is highly reactive to my unique requirements. It's essentially the engineer-to-order of the service world.
But look at the trade-offs on the matrix. In this high-contact environment, your production efficiency is abysmal.
Yeah, true.
It takes weeks of labor. It requires highly paid experts. You cannot automate it. However, your sales opportunity is massive. Because that CPA is sitting across from you building a relationship, they can upsell you on estate planning, audit defense, financial consulting.
The high contact relationship drives immense revenue per client.
Exactly.
Now let's swing to the complete opposite end of the matrix. Low contact, the make-to-stock of services.
Here, direct customer interaction is engineered out of the system entirely. The service is delivered via the internet, an app, or a kiosk.
This is standard online tax preparation software. I don't talk to a human. I just punch my W-2 numbers into a rigid web form.
In this low-contact environment, production efficiency hits absolute maximum. The software can process 10 million tax returns in a single day with almost zero marginal cost per return.
But your sales opportunity during that specific transaction plummets.
Right.
Yes, the software might have a pop-up ad to upgrade to premium, but you cannot have a nuanced, persuasive conversation to sell a complex $50,000 consulting package.
What I find fascinating is watching modern tech companies try to bridge these extremes.
Like who?
Look at Uber or Airbnb. They operate with the massive production efficiency of a low-contact internet app, but they use technology to simulate a high-contact, highly responsive physical service.
That is the sweet spot. But the matrix remains a cruel master. As you decrease direct human contact to gain efficiency, you invariably lose the ability to read a customer's subtle cues and build deep, high-margin relationships.
Very true.
And once you've designed that service, how do you know if it's actually working? Because good service is so subjective. The sources introduce an analytical tool that I think is brilliant, the Service Gap Analysis Matrix.
It's a great tool.
I genuinely think anyone listening could use this tomorrow to audit their own department or business.
It completely cuts through the subjectivity. It plots two simple variables against each other. On one axis, importance to the customer, ranging from unimportant to important. On the other axis, customer perception of service, ranging from poor to good.
By crossing those axes, you create 4 distinct quadrants that tell a manager exactly where they should and shouldn't be spending their time and money. Let's break down the 4 quadrants, using my Mug Genius company as an example. Let's say we launch an app to control the mug's temperature.
Okay, Quadrant 1. The customer thinks a feature is important, and their perception of your service on that feature is good.
For the app, let's say that's Bluetooth connectivity. Customers care deeply that it connects instantly, and my app does it flawlessly.
That is the competitive strengths quadrant. You are winning where it matters. Your management goal here is to maintain this performance and aggressively leverage it in your marketing. Don't over-engineer it, just protect it.
Okay, Quadrant 2. The customer thinks a feature is important, but their perception of your service is poor. Let's say the battery life indicator on the app is constantly wrong and customers are furious because their mugs are dying mid-commute.
Alarm bells should be ringing. This is the critical improvement areas quadrant. You're failing on a core competency.
Ouch.
This gap is fatal. This is where you immediately direct your capital, your Six Sigma quality improvement projects, and your best engineers. Fix this before you do anything else.
Six Sigma being the data-driven methodology for eliminating defects. Right. Now, quadrant 3. This is the trap. The customer thinks a feature is unimportant, but your execution of it is good.
This quadrant is labeled non-value added. You're doing a phenomenally good job at something the customer does not care about.
Let's say I spent $200,000 hiring a composer to write custom, beautiful orchestral hold music for my customer service phone line.
Okay.
The music is objectively excellent, but the customer calling in just wants a refund and doesn't care about the symphony.
You are burning resources.
Yes.
That is non-value added. The brutal recommendation of the gap analysis here is to actively reduce your investment in this area.
Barely cut it.
Stop paying the composer, take that $200,000 and shift it over to quadrant 2 to fix the battery indicator. It is incredibly difficult for companies to admit they're great at something useless.
It takes so much ego to admit that. And finally, quadrant 4. The customer thinks the feature is unimportant and your service is poor.
This is the slight irritations quadrant. It's annoying, but it's not a deal breaker. Maybe the font color on page 4 of the app's terms and conditions is slightly hard to read.
Yeah.
It's poor service, but no one is returning the mug because of it. Keep an eye on it, but absolutely do not prioritize it over your critical improvements.
So we know we need to fix the battery indicator. We launch an internal project to do it. But as anyone who works in a corporation knows, internal projects often devolve into chaos, missed deadlines, and finger-pointing.
Oh, constantly.
The text briefly touches on project management, specifically focusing on accountability.
Right. To execute a project, you need a charter, management support, and most importantly, mathematically clear roles. The tool to eliminate the finger-pointing is the RACI matrix, RACI.
Let's walk through a scenario. Let's say Mogenis is launching a massive project to redesign the heating coil. We are going to use the RACI matrix to figure out who does what.
The letters stand for responsible, accountable, consulted, and informed. The most critical distinction in operations management is the difference between the R and the A.
So let's designate the lead engineer as R responsible.
That means the lead engineer is the one actually doing the work. They are running the CAD simulations, performing the thermal tests, writing the code. They are the hands on the keyboard.
But the A accountable goes to the VP of product development.
Exactly. The VP isn't running the tests. But if the new coil catches fire, it is the VP whose head is on the block. Accountability is the ultimate ownership of the outcome.
And the golden rule of the RACI matrix is what?
You can have multiple people responsible for a task, like a whole team of engineers, but you must only ever have exactly one person accountable.
What happens if I make both the VP of product and the VP of manufacturing accountable?
If two people are accountable, no one is accountable. When the project fails, VPA points the finger at VPB and vice versa. Accountability requires a single throat to choke.
Okay, what about C consulted? Let's say we tag the marketing director as consulted.
That is a two-way communication channel. Before the VP makes a final decision on the coil design, they must consult the marketing director to ensure the new design doesn't alter the outside shape of the mug, which would ruin the planned ad campaign.
Ah.
The marketing director provides crucial input, but they do not have veto power over the final engineering decision.
And finally, I informed, we designate the chief financial officer as informed.
This is a one-way communication channel. The CFO needs to know when the project hits its milestones so they can release budget funds.
Yeah.
But they are not doing the work, they're not accountable for the thermal physics, and you do not consult them on the engineering specifics.
You just tell them, the test is done.
Exactly. This stops the CFO from unnecessarily meddling in the engineering meetings and slowing the project down.
So what does this all mean for you? If we step back and look at this entire journey, the complexity is breathtaking. We started with the highest level boardroom question. Are we guessing what the market wants, or are we reacting to it? Push versus pull.
And that single philosophical choice dictates a brutal cascade of physical realities.
Right. Choosing to push dictates an MTS environment. An MTS environment requires a high-volume line process. A line process demands a linear product-based layout. It is a perfectly interlocked set of gears.
Yes.
A misalignment at any stage is like trying to force an engineer to order a custom product through a continuous flow layout grinds the entire supply chain to a halt, bankrupts the company, and leaves the customer empty-handed.
And as we saw with the service and gap analysis matrices, even in the intangible world of apps and consulting, those exact same laws of physics apply.
Yeah.
The trade-off between hyper-efficiency and bespoke customization is inescapable.
It really changes how you look at the world. You start seeing the matrix everywhere.
You do. But I want to leave you with a final thought to mull over, one that challenges everything we just discussed.
Oh.
We've talked extensively about how these environments and layouts define the modern factory. But look at the technological horizon.
Where are we going?
Think about the rise of localized, hyper-advanced 3D printing hubs, combined with AI that can predict consumer behavior with terrifying accuracy.
Okay.
Will the traditional product process matrix even exist in a decade? Or are we moving toward a world where the extreme efficiency of continuous flow and the absolute bespoke variety of engineer-to-order merge?
Wait, ow.
Imagine a single localized machine sitting in your neighborhood pharmacy. An AI pulls a localized demand signal, and the machine 3D prints a completely custom, perfectly engineered product on the spot in 3 minutes.
The ultimate hybrid, zero lead time, infinite variety, zero inventory.
Exactly. The fundamental rules of volume, variety, and factory layouts that we've relied on since the Industrial Revolution might be on the verge of a complete rewrite.
That is a massive paradigm shift to think about. The blueprint of the supply chain is evolving fast. Tomorrow, when you are out in the world, look closely at the businesses you interact with.
Yeah, pay attention to it.
When you order your coffee or buy a car or download software, try to spot the operational architecture. Ask yourself, are they a work center or an assembly line? Are they pushing inventory at you, or are they pulling based on your demand? The invisible machinery of the world is all there, hiding in plain sight. Thanks for diving deep with us today.